as needed through this, but I just wanted to talk about a couple of the key ideas to make sure we've got them down that are often used in the sorts of problems that we run into, whether it is related to optimization or other sorts of techniques, applications that involve any sort of angles, angular motion, or sometimes just triangles involve trigonometry. So this diagram is set up to represent something maybe with angular motion, so I can think about moving in a circle direction and thinking about all the different angles. And in addition to the trig function values like sine, cosine, tangent, we can also talk about just the circular motion itself. So what we talked about on Friday, it doesn't really matter what size circle I have. If I have this is 1 radian, this n equals 1 here at the bottom, if you can see that. So this 1 radian measurement, what that means again is that, let's get this on here, is that whatever the radius length is, if I'm at an angle that's called 1 radian, the arc of the circle that's subtended by the angle, so this arc and the angle have the same number associated with them, but for the angle, it's an angle measurement, obviously. For the arc, it's a length of this curved line segment, and in each of them, it's 1 radius length. It's just that these circles have different radii. So this largest circle has supposedly radius of 6, so the length of this red line would be 6 units long. If this is an angle, so this central angle here right now where I have it frozen, no, I'm going to write frozen. Central angle is 1 radian. That means that the arc corresponding to it on any circle, when you're at the center of that circle here to form that angle, is going to be 1 radius length. So this outer circle has a radius of 6. So this red segment is 6 units long, same as the radius. Or this blue segment is 4 units long, same length as the radius of the circle. Or this little tiny purple one that we were zoomed in closer to before, since this is a circle with a radius of 1, then that means that this magenta colored line there has a length of 1 also. It's 1 radius length, whatever that radius is. So if I'm at an angle that's not 1 radian, if it's some random number of radians, let me just clear this off, it's messy anyway. Let's see, 2.49 radians is now my angle. That also means that the lengths of those arcs around the circles are 2.49 radius lengths. So this red one with a radius of 6 would be 2.49 sixes. It's 2.49 radius lengths regardless of what the radius is. But in this case, if I wanted to have a better way to say that, like, well, how many inches is that? If this radius is 6 inches, then the length would be 2.49 times 6 inches. So whatever that is, a little bit less than 15. I'll say units in general. Whatever the units of measure for the radius are, the units of measure for arcs around the circle are going to be dependent on the size of the angle that forms them, the central angle there, and just a multiple of that radius. So when we measure in radians, that's why it's very handy to measure in radians. We can directly relate the size of the angle and the arc around the circle that it forms. So let's just stop at this spot right here where I've got this 2.49 radius lengths. Regardless of which of these 3 circles I'm talking about, I'm just going to use the outermost one because it's bigger and easier to see. But this spot here on the circle, on any of these circles actually, has a specific relationship between the x and the y coordinates and this angle. And these are, you can talk about those coordinate points by using our sine and cosine functions. Those specifically relate horizontal and vertical distances from the axes that were graphed on here to the radius length that we have, or tangent function relates just the horizontal and vertical to one another. But in terms of these coordinate points, if I want to talk about the horizontal coordinate, that has to do with the cosine function. And again, if you remember from like triangle trig sorts of discussions, you can think of like a reference triangle if that's something that sounds familiar, and thinking about this angle and adjacent and hypotenuse and those sorts of things. But just these coordinate points here, well, the whatever this angle is here, the cosine value of that angle directly applies to the smallest circle with a radius of 1, but the cosine value relates to these horizontal distances. Sorry, I'm like tracing vertical distances here. These horizontal distances relate to cosine and the vertical ones relate to sine. And so if I wanted to talk about the horizontal distance to the left that this is, if I'm on the smallest, this 1 unit circle, often just called a unit circle, then this 1 unit to the left here that I'm going, or 1 unit to the left that I go to get to that radius, this, you can see that the left is slightly less than the radius. It looks like about -5 or so. But in reality, I can express it exactly by using the cosine function. So on the smallest circle, it's a little less than -1. On the largest circle, it's a little less than well, not less than, closer to 0 than -6. So what this is, it's related to the size of the radius, but they're just multiples of one another as we get larger. So the cosine gives us directly the point on this unit circle. So I could say the cosine of, what do we say, 2.49. So cosine of 2.49 would give us this almost -1 that we have in the smallest circle. If I want to scale it up to a larger circle, just like this arc length, I just multiply it by the size of the radius. So this circle has a radius of 6. So 6 times the cosine of 2.49, that's the horizontal coordinate of this point. This would be a negative number. You can put it in a calculator in radian mode and see that that looks to be like -5-ish. If I want to talk about the y-coordinate, that same spot, it utilizes the sine function. That, like, again, if you're thinking about triangle trig, it's that sine is opposite over hypotenuse and that sort of thing. But we're talking about the y-coordinate here. I want to know not what the sine function is, but I want to know what is this vertical distance here. This vertical distance is, well, it's quite a bit less than 6, but each one looks maybe about like 2/3 or so of whatever the radius is the height above that horizontal axis. But what that ratio is, that's the sine function. So I've got the sine of 2.49. That would be the actual height of a unit circle, or a circle with radius 1. But when I have larger circles and I'm scaling up, I just use the radius to do that. Or I have 6 times the sine of 2.49 would give me the height here. But you can also estimate, like instead of saying, oh, it's 6 times cosine of 2.49, if you needed it just to, if you have a sketch of a circle like this, you can say, let's see, it looks like about -5, 4. Or, yeah, -5, 4. And if you test in the values of this, 6 times cosine of 2.49 and 6 times sine of 2.49, they'll be close to those. Not exact, but just in terms of, are you doing something reasonable with trig? Keep that in mind. Or in general, for any circle. So this 6 was just the radius of this largest circle. In general, the relationship that we have, if you want to describe xy points around a circular arc, the x-coordinate in general is going to be the radius times the cosine of the angle, whatever that central angle is. And the y value is going to be that radius times the sine value of the angle that forms, the angle that goes through that point. The terminal side of the angle passes through that point on the circle. So how this relates to the whole triangle thing, those were solved for the trig function. X divided by r would be the cosine function of angle theta. And if you think about that, oh, that's adjacent and hypotenuse. Adjacent over hypotenuse is cosine, and if you have those stuck in your head from triangle stuff, and that's fine, whatever helps you remember. Again, y over r, just rearranging these, would be the sine function. Sine function is defined in triangles, if you've seen it defined that way, as that opposite over hypotenuse. So the length of this side divided by the hypotenuse. Just the only thing with triangles and why I picked an angle over here is those don't generally involve negatives. So triangles have to have positive length sides and so forth, but you can kind of imagine where this is actually my angle over here that we were using, that 2.49 radians is measured from the positive x-axis and going around counterclockwise. In case that's how we measure to get this 2.49. And then these results here, this x value just as it is, will come out negative. Y will come out positive. So in any case, so there's arc lengths and coordinate points, sort of lengths that you can talk about, like a distance to the left or a distance vertically above or to the left of or the right of an axis. Yeah?
Why do you still use the larger angles as pi minus the 2.49 to the
We don't have to do any sort of angle conversion. We'll just use the actual angle that's there. Yeah, so the angle that's here, the one that formed, like this angle here, if we do the sines and cosines of it, it gives us all the positives and negatives. If you use the smaller angle, the reference angle, the one that's in the triangle, it won't give you any positives and negatives. It'll just be all positive. So you can just use the actual angle. Like in trig classes and pre-calculus, there's lots of different things that you do with trig, including like evaluating manually things like sine of pi over 3. And we're not going to focus on, do you know what all these reference angle sorts of values are off the top of your head in terms of square roots and stuff like that. That's not our point. Point is to be able to write the relationships between the angles and the arcs, or the angles and the distances that they form in various directions, so that we can solve new and different sorts of problems instead of always dealing with geometry and volumes of boxes and areas of, or surface areas of cylinders and whatever else you're working on. So I hope that you had a chance over the weekend, first of all, to complete the assignment that was due a couple days ago on critical values, but also maybe to look ahead, and if you haven't done so, start looking at it. The next homework assignment in Math AS, the homework number 14, I believe, is about optimization, and there are a bunch of questions. So I think there's 12 of them. The last several of them involve optimization and trig functions. But in any case, I do want to go over an example of an optimization problem today using trig, setting this up, seeing the same sorts of relationships in a setting where there's not just how do you describe this coordinate point, but how do I set up a function whose dependent variable is going to be something that I'm trying to maximize or minimize. All right, so let me clear this off. And let's see, I'm looking for pond. Let's see, I had one that was nicer. Hold on a second. Should have left that open. Pond. There we go. So there will be a take-home quiz this weekend, by the way. I'm going to post it today, but I'll pass out copies of it on Friday so that you can have a paper copy made by me if you want, but you can see it in advance and whatnot. But I'll post it shortly after class. All right, so in any case, here we've got a circle. Let me show you the details of what the problem is that goes with this. And I'm going to make this bigger for a moment so you can possibly read this. And go away. All right, so we've got a race coming up. The first part's just kind of a description. The second part has some of the numerical details here. But let me read this to you. In the middle of an upcoming race, competitors will approach a pond obstacle. A circular pond with radius 1.8 kilometers is directly between competitors and the finish of this race segment. To finish the segment, racers have two options. They can swim all the way across the pond, or three options rather. Swim all the way across the pond, run around the shore of the pond, but it's rocky and treacherous, so not necessarily easy. Or three, do any combination of those two. So let me show you the picture, and then we'll get to the other details. So we've got, here's our circular pond with a radius of 1.8 kilometers. Runners are approaching from the right side of the screen there to that orange dot. They could just swim right across. Obviously, swimming straight across instead of swimming in weird circles would probably be easiest. Since it's a small pond, there aren't tides or anything. So they could swim across. That'd obviously be the shortest distance, but we've got some details about speeds yet to come. Could run all the way around, like one way or the other, doesn't matter. I just picked the top half of this as where the running might take place. But that would obviously be longer. Or you could run part of the way and then swim the rest. You could obviously swim first and then run, but I figured maybe your feet will be less slippery if you do the running on the running first on the treacherous rocks. So we've got a bit of time to plan for this race. Erin knows she can run the rough terrain at 4 kilometers per hour and swim at 3 kilometers per hour. She figures she can probably do best by running part way and swimming the rest, but she has a week until the race, so we'll plan a strategy in advance. So she drew the diagram below to represent the path she could take, and her goal is to get past the obstacle as quickly as possible. So let me shrink this a little bit. So our goal is to get past this as quickly as possible. And again, the radius is 1.8, let me just write that on there, kilometers. That's the only number from the top half of this. So this is a long problem, very different from the other ones that we've worked on. There is geometry, I guess. It's a circle, but we're not finding its area or anything like that. Our goal in this problem, make sure when you read a question, you know what it is that you're trying to accomplish. So are you trying to find a rate of something? Are you trying to find a maximum of something? Are you trying to find what are we doing? So are we trying to find a maximum or a minimum something here? Her goal is to get past the obstacle as quickly as possible. Yeah, so get past something as quickly as possible means we're trying to minimize, and what quantity are we trying to minimize here? Time. Yeah, so we want to minimize the amount of time that it takes. So make sure, even though that seems simple, it's really easy if you just like see a problem like, oh, distance, I'm going to write a formula for distance. Like, well, distance is involved for sure, but we actually want, in this case, a function, if we're going to try to minimize time. We want a function whose output is time. So time is related to distance and rate, and we can see that there are certain rates we can use. But our goal here, make sure you remember what this is, we're going to try to minimize the time to complete the race. So this is just an example of a path, but in reality, this orange dot here doesn't have to be up there. It could be, she could just swim a little, or just run a little tiny bit, then swim, or maybe it's run a long way and then swim. Maybe it's somewhere half and half. Maybe it's swim the whole way, maybe it's run the whole way, but that would be covered if we set our domain properly for what we want to do. We want to set up a time function somehow. We can get some formal variables in a minute, but if I want to describe how we'd compute how long it took Erin to run this, can you see that there would need to be 2 parts to the function? 2 different parts, because she's got 2 different speeds, right? So the time that it takes her depends on how long she runs around the edge and then how long she swims. And I'd probably separate those out because that's going at 2 different speeds. So I'm just going to put time running like this and time swimming, just making up temporary variables just to kind of make an idea in my head of what I want to do. So we're running and swimming at 2 different speeds. We're trying to figure out how long something takes. So distance and time and speed, rate are all related. If I have a relationship in mind for distance, rate, and time, and I get it to tell me something about time, what time equals, what would that expression for time be in terms of distance and rate? Let's see, because most people have it memorized, it's just kind of in your head as a different order, or we've used it kind of a lot of times in a different order in here. Usually distance equals rate times time, or if I want to know, like how much I accomplished, I use my rate for a little bit of time and then something happens. So I run for a little bit of time and then something happens. But I want to have that same relationship solved for time, have the t by itself. So if distance is rate times time, then time is going to be equivalent to a division problem, yeah? What goes on top? Distance over rate. Yeah, so if I have something like miles per hour on the bottom, like miles on the top and miles per hour on the bottom, that would give me hours by the time I'm done. In this case, we're going to have kilometers per hour and kilometers and hours if we don't want to do any unit conversions, which I just assumed we didn't. So just a general relationship between distance, rate, and time in terms of time, solved for time, would be this sort of expression. So if I can figure out, going back to this, I've got two different rates. If I can figure out the distance that she runs, or an expression for this general distance that she runs, and divide that by how fast she runs, and the same with time, or with swimming. The distance swimming divided by the rate swimming. A couple of those are constants that we know. The rate at which she runs and the rate at which she swims, those are just numbers in the problem. The distance that she runs and the distance that she swims, that depends on where we put that middle orange dot, right? So that's going to be most of our work in this problem, and one of those is much more challenging than the other. But again, our overall goal, we're trying to minimize time. And so since time is related to distance and rate, and I've got two different rates, here, I'll abbreviate this. Distance running divided by the rate at which she runs was 4 kilometers per hour. And then the distance she swims divided by 3 kilometers per hour. So this is looking better as a formula. Now I just have to come up with two expressions for distance. One of them, not too hard, is just an arc of this circle here. That's how far she's going to run. Now this is just a general picture. This orange dot could be lower, could be higher, but so I'm not going to guess a number for anything, but if you can imagine, let me just call this angle theta, like we've been doing. If I call that angle theta, think about what is the distance that she runs in terms of theta, or as a function of theta. She goes around this circle that has a radius of 1.8 kilometers, travels around an arc that subtends an angle of theta radians. What's the length of the arc? 1.8 times theta. All right, this is looking better. So I've got this first half of the expression here. 1.8 times theta, not 1.80, this is 1.8 times theta, that distance, divided by 4, which is like 0.45 theta or something. That would be the running half. Now, the swimming half, not half, running part, and then the swimming part, let's say. So now we've got a bit of a trig problem to think about. I'm going to start it and let you think about it for a little bit longer. But if I want to know how long she's swimming, notice that in this picture, this is not a hypotenuse of a right triangle, at least not yet. It could be if we draw the right triangle, but it's some random line, a chord of this circle. And this angle that we just drew isn't related to it, but somehow I need to use this angle still so that I can have the second part of my distance based on the same variable, because I really want to have a function that only has one variable in it, one independent variable. So if I want to know the length of this blue segment, think about making a right triangle. Theta's in that right triangle, kind of. It can help us with aspects of it. But take a couple minutes and see if you can come up with a way to express the lengths of the sides of that right triangle or its hypotenuse which would be the distance that she swims. Hypotenuses of right triangles should be something that, like, there's a formula for finding the length of that. But take a couple minutes. And think about how parts of that triangle are related to trigonometry. That was in the first paragraph of the problem. Yeah, the 1.8 kilometers was in the first paragraph that I scrolled past. Yeah. This coordinate point that I just bubbled in, by the way, should know how to express the coordinate points, x, y values for that in general. So that means we know some things about the triangle. What would be if we consider the center of, coordinate point. If I consider the center of this circle to be the origin, what would be the coordinate point, the x coordinate for this circle? How far to the right of what would be the vertical axis would this be? Yep, 1.8 times sine or cosine for horizontal? Cosine, 1.8 times cosine of theta. Now in terms of this triangle, that would be this distance here, 1.8 cosine of theta. Just this bottom side of the triangle. Sorry, that looks like a blob. 1.8 times cosine of blob is the little section over to the right of our, well, we're trying to find the hypotenuse of the blue triangle. What's the rest of that bottom side length of the blue triangle? The part to the left of that center dot. 1.8, right. So this section is 1.8, and these measurements are in kilometers. So I've got 1.8 kilometers for part of the bottom, and then the portion on the right, to the right of the center of the circle, is 1.8 times the cosine of theta. And the height of this triangle measured from, assuming this is through the center, we can imagine this is the x-axis here. This height would be 1.8 sine of theta, measured in kilometers. So where the distance is 1.8 times the sine of theta, kilometers. Well, now I know the bottom length altogether of the blue triangle, and I know the height altogether of the blue triangle. I should be able to find then its hypotenuse length using the theorem that nobody forgets, Pythagorean theorem. So going back to, let's see, let me put this in blue. So this distance that she's swimming here would be the length of the hypotenuse. A squared plus B squared equals C squared. We just want to find C. So square root of each side length squared. So just one of them is a mess and one of them is not quite as much. 1.8 sine of theta squared, and then 1.8 plus 1.8 cosine theta. Now, guess what I'm not going to have you do after this? I'm not going to take a derivative and set it equal to 0 and whatnot right now, because this is starting to look like a mastery test example, and I'm not sure. We might be looking for places where it's undefined, actually. Let's see, 1.8 plus 1.8 cosine theta is the bottom side length squared plus the vertical side length squared. Square root of all that should be our hypotenuse length. So let me just, I'll abbreviate this over here. But our whole formula is this 1.8 theta over 4 plus this lovely distance here over 3. And that's a function for time that it takes her to run this in terms of theta, the angle that's marked there. So we could also describe it in terms of, if you want to say, okay, you're going to run to such and such point. When she goes to map this out, she's going to try this in advance. If she solved for what the ideal angle theta is, she could run around and see what the surrounding area is, so she'd know, because she's not going to be able to jump to the middle of the pond and measure out an angle while running this. But trying to map this out in advance, you can plan for something like this where we have this time function that's extremely unpleasant, and yes, you could take the derivative of it. Do we want to bother with the algebra afterward, or can we just stop with our trig skills and say, this is the 21st century, let me have technology assist me with this? So let's have technology assist us with this, but before I erase any of this on here, I just want to repeat what we've got. Our goal here in this problem, we had this circular obstacle that we're going to go around part of it and then through part of it. Potentially, we don't know quite what angle this is. Maybe the angle turns out to be, what should we think of as limits, domain for the angle, the independent variable? What would be the smallest angle that I'd need to consider? 0 through, let's see, well, yeah, through pi radians. Pi radians is exactly halfway around a circle, angle-wise. We could keep going, but it would just either take us to maybe the bottom half of the circle or the top half again. So 0 through pi is fine for this. So here's our function. Maybe I'll call it t of theta, where theta is restricted to just 0 through pi, where an angle of 0 would indicate that she doesn't run around, just swim straight across. And an angle of pi would indicate we go all the way around running and don't bother swimming. And everything in between would be covered, and we don't need to worry about the bottom half of the circles because it's a circle, symmetric paths, etc. So we have this time function. The reason we wrote time, we're trying to minimize the time that she spends getting past this obstacle because she wants to win the race or get her best time or whatever. So we have time based on the two different speeds, so we separated into two parts, time running and time swimming, and related those time expressions to distances and rates, which rates were given in the problem, distances we can compute or express using trigonometry and mystery angle, but the angle is the thing that we can vary here. We can have the angle be as small as 0 or as large as pi, and anything in between would give us different values for these, but they're the same relationships, regardless of which angle is chosen. So going on to, this is where technology can assist you. Now, this one is actually possible. You can solve it manually, involve some trig identities after doing a horrible derivative. I mean, it's not the worst derivative. That's not too bad compared to some things that you saw on the mastery test, relatively. It's about the same as some of the horrible ones. But the algebra afterward is just a lot of algebra and some trig identities to keep track of with, it's Pythagorean identities. But let's take a look at the meaning of this and see what all of this has to do with. So I'm going to clear this off so that it doesn't show up elsewhere. and pond. Here we go. So here's our expression that we had. Only I just used x instead of trying to type in a theta since it's easier to type. But if I want to know what this function looks like between 0 and pi, then I can just say, okay, well, this is a function, this is my time. So I want to graph my time and find its minimum. I want to graph y equals f of x from 0 to pi. And I didn't put the or equal to's in there, but it will look the same. That's just extra button pushing that I didn't want to spend time on. So, that doesn't look too interesting. It goes up and back down. So my goal is to minimize time. Just visually inspecting this, where does it look like the minimum time occurs? Time, remember, is a dependent variable in this graph. This isn't the derivative. At the beginning, right? This looks like the lowest point in the graph. It looks to be about 1.2 or so. And then this time goes up as the angle increases to around 1.5 or probably pi over 2. We're a little bit above 1.5, which would be time in hours. And then it decreases again down to maybe about 1.4 hours. But it looks like the lowest point is at 0 for x, meaning 0 radians around the circle. So back to our picture, which no longer has writing on it, but let's see, here we go. If 0 was our angle, that means that this dot is actually down here. Or her optimal time, which is about 1.2 hours to get past this obstacle, is to run until I get to right where I started, run nowhere, and just swim straight across. So if you had done all of the calculus and the trigonometry and worked to solve this and found that out, you'd probably be really angry that the answer is just swim. But if you set this up and figure it out, rather than just like trying to run the race and spending an extra 0.2 of an hour doing swimming stuff and being all wet, you'd probably be more upset. So it's a trade-off, but like I said, technology can be our friend. You don't have to avoid it entirely, but at this point, by the time we did all of the high-tech setup and we understand what needs to get done, just the actual, like if I wanted to find a derivative and set it equal to 0, or in fact, let me show you what happens with this. Where is this? If I take off this domain restriction here, you see there's nothing fancy about the point 0. It's just on the way up. But before 0, that's that kind of nonsense, because that would be her swimming negative kilometers or something. Negative hours, I guess, or fewer hours from having swum negative kilometers. But 0 to pi is the part that makes sense. Right at pi, there's actually a corner point you can see where this function has a quick corner, so the derivative or rate of change would be undefined. So what's actually going on here, this is like if she swims or like runs all the way around the circle more than once and then swims through it, that's obviously going to take longer. And we don't want that to happen. We don't want to run around more than half the circle and then start swimming. That doesn't make any sense in terms of the race. People would probably check to see if she had enough water. Whatever. But so this is the only part that's important to us right here between the x-axis and this first corner point, which happens, as you can see, just past 3. That was our end of our domain there when we put in 0 through pi. But it turns out, after all that, you do have to have a lot of knowledge of what you need to do here. It's mostly trigonometry in this case, if we just stop at this point and don't do the calculus, but realizing that how we have to set this up is to use all the different relationships between rates of change, our time and distance, and then the goal, it just happens that it turns out to be very tedious this time. The goal would be to figure out where the function has maximums or minimums. In this case, like I said, just turns out to be angle 0, which corresponds to don't run, just swim. So in any case, that's our fun with trig. Just want to give you an example of one that's a lot harder than the ones that are at the end of your assignment. In the iMath AS assignment, let's see. There we go. So the one that's due on Monday the 19th. So, or yeah, homework 13. I think I called it 14 before. But number 13 is about optimization. 14 and 15 are things we're going to start talking about. Maybe I'll talk a little bit about 14 right now. But 15 is definitely a Friday and next week sort of thing. We'll talk about this, but it's a different sort of structure related to taking derivatives of other types of relationships that maybe have more variables than you're used to, or things that you represent by a variable, but you realize it's actually an entire function. So we've got kind of chain rule going on in places where you might have thought it was just a Pythagorean theorem. But in any case, this homework number 13, just quickly, there are 12 problems. Let's see, I think it starts with 10, 11, and 12 all involve lots of trigonometry. So what I need you to do on this problem, do all of the questions if you can, but you can skip any 2 questions you would like and still get full credit. So this is listed as being out of 24, just because it's Math AS and it does that. But when I put it into Canvas, it'll be out of 20. So you can skip any 2 questions you want, or whatever, and you can still get full credit. So there are a possibility of 4 extra credit homework points essentially on this if you complete the whole thing. So that's essentially, if you want to just do 1 trig problem, you can do that and skip the other 2. There's this one that involves angles of folding, like angles for a rain gutter and maximizing the volume, which just as a point on this, I wanted to mention this. If I want to maximize the amount of water that can go through the gutter, this is a side view of like a gutter that is on a house. We don't have these a lot out here because it doesn't rain. But if you're from anywhere else in the country, you know, at the edge of your roof, there's like places where the water runs down and it catches and it drains down to one particular spot so it doesn't turn into a waterfall at the edge of your roof. But we want to maximize the amount of water that can flow through this. So that's really, we want to maximize the area inside these pink curves here. So just in case that's not a, rain gutters aren't a concept you're familiar with, we want to maximize the area that's inside this cross-sectional area of it so that it can hold the most water by adjusting these angles. So what angle should the metal be bent at so that the trapezoid here, the trapezoidal cross-section, has the greatest area. The other questions, kind of fun. This one you can maybe imagine might involve some either similar triangles or Pythagorean theorem. There's lots of different things we can relate in these. The last one has a cow staring at a nearsighted cow problem. It's a cow staring at a billboard, and I'll let you read it. But they're interesting questions, I think. Kind of bizarre assortment of things. They're not all just like maximize the surface area of a cylinder, but here's a field getting divided in half with fence. We've got cans constructed of whatever. There are a bunch of geometry questions first with area, surface area, volume sort of things. But then the last 3, 10 through 12, involve some trigonometry, and things related to trigonometric functions are going to be involved because we do need the angles in addition to the lengths. So in any case, here, let me just show you what we're going to be talking about on Friday, because we've just got a few minutes left today. Let's see. So here's a funky curve. X squared plus y cubed minus 2xy equals 7. So that's the typed in. It has x's and y's in it, so GC wants to graph it. This is the set of the coordinated pairs x and y that make that statement true. Now, as you can see in here, this is not like a normal sort of thing we've worked with before. The dependent variable is not a function of the independent. Y isn't a function of x in this picture. You can tell by the things like, you know, any independent variable value, there's, in some cases, more than one different dependent variable value that goes with that. We're going to be talking about derivatives, dy dx or d whatever dx. Pick whatever 2 letters you like. This one has x's and y's in it, so I could find dy dx or dx dy. The rate of change of one with respect to the other. We should still be able to do that, because if you can imagine, like looking at this, like, all right, so in this picture, I can see there's a point here at -2, comma, a little bit less than 1. And if I wanted to talk about the rate at which y changes with respect to changes in x, I can see that, well, if I zoom in close there, it looks like an essentially constant rate of change. So I should be able to, A, estimate a derivative value or a rate of change value of y with respect to x. B, I should be able to come up with some sort of formula to do that in general. Now, I said formula instead of function because not a function in the standard sense of y is a function of x. But if I call the derivative of this, I'll call it just dy dx since I don't have function notation. I don't even have y as a function of x. But looking at this shape here, like I should somehow be able to express rates of change of y with respect to x. And at points like this, it's like, oh, well, easy. I could sub in -2 and I could get a rate. Now, if I went to like x equals 3, the only issue is, the only way this is really different from, I mean, the formula certainly looks different. The relationship between x and y isn't solved for either of the two variables. It's just expressed that way. But at any of those 3 points where x is 3, I should be able to explain what the rate of change is because each of those 3 points looks nice and smooth. If I zoomed in, it would be essentially linear. It's just that unlike the functions we were dealing with before, here in this y isn't a function of x, just this general xy relation. In order to specify like which point I'm talking about, I would need to know both the x and y coordinates. But if I specify, oh, at 3, 2.25 or something, maybe that's this one. If I sub in x is 3 and y equals 2.25 to some magic formula, it should give me this rate of change. I don't have that formula just yet. We'll work on it. But if I sub in x equals 3 with a different y that also happens to make this true, or x equals 3 with a third y that also makes that true, I should clearly get 3 different results. But I should be able to come up with an expression for this rate of change of x or of y with respect to x. It's just that because of this issue where the dependent variable y isn't a function of x, in that sense that each y value there's a unique y value for each x. Since it's not that way, the formula, the function rule I'm going to have for this dy dx is going to need us to tell it both x and y values because otherwise it doesn't give us enough information. So what we're going to work on, and part of your assignment between now and Friday, is to read, it's actually part of back to chapter 6, I think it's like 6.3.9, about implicitly defined functions. That's what this is called. Implicitly defined functions or implicit relationships are things where we have a dependent and independent variable idea, but they're kind of jumbled together and I can't necessarily separate them, or maybe I just don't want to, because we can find derivatives of one variable with respect to the other, even if they're mixed together in the middle of an expression. And it involves thinking about using chain rule in a slightly different way. So, in any case, I'll leave it at that for today. You'll have reading assignments, working on Math AS, and I'll post a take-home quiz that'll be due next Monday. I'll post it early so you can get a head start on looking at that. But I will see you later.